Yeah, well, I've hooked up my iPad, so I can basically have my own little whiteboard here. So
beautiful. Yeah.
Right.
Yeah, I guess we should probably start just because the slightly lower number is also a reflection of we're probably losing the Europeans and the people from Asia and such. Okay, so let's begin. This is today. This is a lecture, our last lecture of the day, regular lecture of the day, but please don't forget about the public lecture tonight at 7 p.m. Boulder time by Wolfgang Ketterle. So the lecture now is by Meera Parish, coming to us from Monash University. And I guess for Meera, it's Wednesday morning. So thank you so much for being so accommodating and with your time and getting up early to give this lecture. So Meera is going to give a series of 3 lectures. This being the first one on BEC-BCS BC crossover and beyond. So take it away, Meera.
Yeah, thanks, Leo. Yeah. So so as you can see from my title slide, you can see where I'm coming from. I'm from all the way in Melbourne, right down the bottom of Australia here. So it's quite a long way away. And here's a nice little picture of Melbourne over here. So hopefully at some point when everything is a bit more normal, some of you guys can come visit. So I'm a theorist, condensed matter theorist at Monash University, Melbourne. So as Leo said, I'm going to give some lectures on the BCS or BEC to BCS crossover. So maybe I'll start just with my introductory slide here. So the motivation of, so what are the basics of the BCS to BEC crossover, or alternatively BEC to BCS crossover, depending on your taste. So really it's describing different regimes of pairing between fermions. So what you're imagining here is you have a Fermi gas, 2 different types of fermions. So here in my little cartoon here, I've denoted them by different colors, or they could be two different types of atoms, two different types of spin states. And the idea is now you're imagining you had an attraction between your fermions, between your 2 different types of fermions. And in the case where you have a very strong attraction, you form these very tightly bound pairs. And okay, so these are now bosonic, these composite bosons. So as you've been learning about, or as you already know, if you have bosons, the ground state of a Bose gas can condense. So on the one hand, you have this Bose-Einstein condensate of dimers, of fermionic pairs, tightly bound fermionic pairs. And now the idea is that as you say, now you can imagine decreasing the attraction between pairs, between your fermions, you can smoothly cross over to another regime over here, which is called the so-called BCS regime, which is named after the situation that you have in a superconductor, essentially, where you have these very weakly paired fermions, where the pairing size is much larger than the interparticle spacing. So this powerful idea of how you can have this crossover between these different pairing regimes, and smooth crossover in the ground state. And we're going to discuss obviously more about this later. But I thought I should just emphasize that the reason why we're interested in studying this type of crossover, these type of different pairing regimes, well, firstly, I think it was a major triumph of cold atomic gases that they were the first to really realize this crossover. This is something that had been predicted and discussed for many decades beforehand. So this was the first realization of this type of crossover between different types of fermionic pairs. And the other thing is that so one of the first experiments, well, perhaps the first experiment, was actually at GLA in Boulder. So the other thing is that it's very relevant to a range of different systems. So first was discussed in the context of solid state system superconductors and semiconductors, but it's also even relevant to neutron stars. So where you have pairs between neutrons and a neutron star. So it's quite a range of systems in which this phenomena crops up. Actually, what's interesting, there's even discussion about how it could be relevant to new types of lasers that are based on, or involve light matter objects called polaritons. So it's even turning up in that context. So it's quite a universal idea of this crossover between different types of pairing. Okay, so what I'm going to do actually is, we're talking about pairing between fermions. So what's important to first nail down is really the two-body physics. So what I was going to start with is a little discussion about two-body physics, scattering theory, and how you can realize this, in cold atomic gases with the so-called Feshbach resonance. Okay, so I'll just outline that. I suspect it might take most of this lecture probably to discuss this, but it's really important to kind of nail this down before we actually turn to there's a many-body physics of what happens in this BCS to BC crossover in the ground state, also finite temperature, and finally let's see how far I get, but finally I'm going to talk a little bit about what happens when you start imbalancing the two types of fermions, the so-called spin and balance Fermi gas, how you can have quite new kind of phase transitions and so forth. Are there any questions about this at this stage, or shall I kind of launch into my...
I had a quick question.
Yep.
Which was, are there interactions between pairs as well, and will they become relevant, or are we...
Yes. Yeah, no, that's a good question. Yeah, so they can, yes. So in general, there are interactions between the pairs themselves. What you find actually, if you go very far into this regime, like very deep into the BEC regime, that the interactions become very weak. But yeah, so in general, there will be interactions. Yeah.
Okay.
But this is like, yeah.
Thank you.
Yeah. Any other questions or no? All right. So let's start with the two-body physics. So I'm imagining I have just, say, my two types of fermions, so two distinguishable particles. Here's my red and blue particles here. So what I want to do, so let's say I go to the center of mass frame, okay? And in that case, I just have a one-body problem, right? Okay. All right, so in that case, what I can do is if I write down my Schrödinger equations. Okay, so let me just set my kinetic turn. And with energy here. All right, so this R here is just the distance, the relative distance between my atoms. And okay, and this here now, this mass here is the reduced mass, right, in my two-particle problem. And now here, this potential here, this interaction, so this is the interaction between my two atoms. So I'm imagining that, firstly, this is rotationally symmetric. So it doesn't depend on any angles, which is the usual, which is usually the case in the problems we're interested in. And also, I'm going to assume that it's short ranged, and I'll come back to this in a moment, what I mean by that. Exactly. So short ranged, rotationally symmetric potential. And okay, my energy here, when I'm going to start by thinking of the case where I have scattering between my particles. So I have my energy here, which I'm going to take to be positive, greater than zero initially. Okay. And so what I can do here is, because this is my 3D equation, what I can do is if I just consider the radial part component. Okay, so I take, so here's my radial part of my wave function. Let me call it just R, capital R. And I'm going to define it, rewrite it in terms of this U, where I've just divided out this distance R here between my particles here. Okay, and so now this satisfies a 1D equation. Okay, just in the radial part. Okay, so I have, kinetic part, and now I have this extra part here. And my potential here, so remember my potential only depends on the R, so that stays the same, and then I just have this here. Okay, hopefully my writing is more or less legible. Right, so okay. And so now, okay, so it basically looks like your standard 1D equation. Now what you have though is this centrifugal barrier term here, which depends on the angular momentum of my scattering. Okay, so I have my angular momentum quantum number here, this L here. And now the key thing here is that if I assume that my scattering is low energy, so in other words, so low energy, I mean, if E is much smaller than the energy set by the range of my potential. So let's say my range is, typical range of the potential is R0. So that's basically the range beyond which I can essentially ignore the effect of my potential. So yeah, so this R0 is the range of my potential, let's say interaction. Okay. So if I assume that this energy is much smaller than this, quite low energy, then what you can see now is that this energy, this term here, will sort of dominate long before I even hit this potential here. So if I'm imagining my particle coming in, so this term will be much larger than the energy here will encounter this term. This term will become very large once I hit the range of the potential. So because that's basically going to be set by this here. Okay, so in other words, with these kind of energies, I can't get past this barrier and experience this this potential here, unless I have L equals 0. So in other words, I require, in the low energy case, so to I only see experience potential if L equals 0. So in other words, once I have no centrifugal barrier here. So this is the low, basically this is the S wave scattering here. Okay, so this is, maybe you've already come across this before, but this is something that that you might have heard stated before, that if you have low energy scattering, you only have kind of S wave scattering, and this is precisely because of this point. So actually, I should mention, when I talked about this potential being short ranged, I was already assuming that it falls off faster than 1 over R squared, or even faster than that, actually. So this potential falls off much faster than the centrifugal barrier here. Okay. So the other consequence of this actually is that if I were to have identical fermions, so instead of having these distinguishable fermions here, they were the same, then due to the required anti-symmetry that from fermionic statistics, so I would require the scattering to be in the p wave channel, so for L equals 1, or odd angular momentum. So that means that if I have low energy scattering between identical fermions, they don't see it, they're effectively not interacting, right? They can never actually penetrate that centrifugal barrier and see this interaction. So that kind of is explaining this statement that often is made about how identical fermions, say in a gas at Fermi gas at low energies, do not interact. Okay. Is there any questions so far about that? It's all clear?
So I have a question for the atoms in cold, for cold atoms that we might be thinking about here. What is a typical R naught, and how should I think about what sets that scale?
Okay, yes. Yes, so in cold atoms, so typically in cold atoms you have these van der Waals interactions, which scale like 1/6. So definitely much faster than drops off much faster than this centrifugal barrier. And there, I guess, what sets the R naught is this so-called van der Waals range, where I guess, let's see, let me see if I remember it. Where I think it's basically where you compare it's comparison of the kinetic energy and the it basically set by when the kinetic energy is, I guess, the same as the strength of that van der Waals interaction. If I remember correctly, that's what sets the range of your potential. Yeah.
Great. And so there was a related question about this. So somebody pointed out that we heard about the van der Waals radius yesterday from Eric, and we've been hearing about van der Waals potentials from Antoine. So it all connects here. There was a question from Garrett. Do you just want to ask your question, Garrett?
Yes.
I remember this derivation from somewhere before, but is R not related to the scattering length at all?
Right. Okay, we're going to get to that actually. So no. So the answer is, well, okay, let me put it this way. It can be. It can be related to the scattering length if we don't have, if we have actually in typical situations, yes, it can be. But the situations we're going to be interested in, the scattering length is going to be actually much larger than this range. Yeah, and we'll come back to that because we're going to be looking at so-called resonant scattering. So in that case, so I'll get into that in a moment. But yes, no, that's a good question. Yeah.
I had another question. So you said identical fermions are basically non-interacting due to the P wave thing, but we also hear about Fermi-Hubbard models where you talk about strong interaction. So where does that come from?
The strong interaction. Right. Yeah. So what you're assuming there is that you're in the situation where you have two different types of fermions. So I should stress that. So if I think what you're referring to is the case where you have these strong kind of interactions between say spin up and spin down fermions. So it's possible to have strong interactions between distinguishable fermions. So different types of fermions. It's just only if they're the same. So if these were, say, both red or both blue, then they wouldn't interact. Does that make sense?
Yeah, I'm just thinking, I don't know if I thought that even like spin polarized fermions might be strongly interacting, but I guess they're not.
Well, okay, you can have, so I'm not looking at this particular situation. You can have P wave resonances. So you can have situations where they are strongly interacting. Yes, that's right. What I'm going to be considering though is I'm going to be away from any kind of resonances in other angular momentum channels. I'm going to be only looking at the S wave case. So I think the statement maybe is generically speaking, if you just took some random potential, generically you won't have a resonance and you'll have no essentially vanishing interactions at low energies. So there can be special situations where that's not the case, where they can be strongly interacting. I should say even with P wave resonances, if you go to very low energies, you still kind of it gets suppressed. But does that kind of answer your question?
Yeah. Yes.
Yeah.
I mean, in a Hubbard model, you could also have different on-site states. You can have two-band model or something like this. So then, fermions can hop between different state. There's more than one state per site, so then they can interact.
Yeah, I guess I thought the Hubbard model was just usually a single band model, but if you had extensions.
Simplest case, yeah.
So I don't know what kind of models people were talking about, but so far, or whether they've talked about lattice models, but
none so far.
None so far. Soon, okay. All right, cool. Right, okay. So far, yeah. So for our purposes, yeah, like as Leo is saying, we're going to think of this R naught as kind of different, separate from the scattering length, as we'll see in a moment. In fact, we're going to basically send it to 0 in a moment. Right. So let's analyze the different parts of this equation. So if we have R larger than this range here, okay, so we can ignore the potential in that case. So that's outside the range of the potential. So oops, I just realized in my equation I've got my U. Sorry. In here. All right. So yeah, so ignore that. So then now we just have okay, so we have our second derivative. I'll just move all my stuff from here over to this side. So just put it on and move my energy term over here. Okay. And remember, I've got rid of this term now. There's no barrier. I'm only considering S wave. Okay, so I have this 2mR h bar squared. I have my energy, and then I have my U here, and that's equal to 0. So yeah, so we've just ignored the potential in this regime, okay, outside the range of the potential. And in this case, then you can solve this equation. Okay, so the general solution is just going to be U of R equals some kind of constant times a sine KR plus some phase shift K, okay? Some real phase shift here, right? And now what the point is now, if I didn't have any interactions, okay, so if this term were absent, okay, so I would just basically send this R naught to 0, so I have no interactions. Then you can show actually, so no interactions. Then that means that the boundary condition for this, you require the boundary condition at R equals 0 to be 0, okay, because otherwise, because you remember that we've defined our, this is the actual wave function. I've got U of R divided by R. Otherwise, I would have a singular wave function if I didn't require this boundary. It didn't have this boundary condition, okay, for no interactions. Okay. And in that case, if I apply that boundary condition, what I find is that that this phase shift here is 0 in the absence of interaction. So this phase shift now that we have here is purely due to the fact that I have an interaction here. So as soon as if I switch on my V here, my short range potential. Okay. All right. Yep. Do I hear any question? All right.
Maybe I'll ask a question, just a clarifying question. So why is there a requirement that R, capital R, be finite? I mean, I can imagine that it's diverging, but it's still normalizable. Is it because you want also just, I guess, kinetic energy? It's derivative you want to be finite as well.
Yeah, no.
Finite, I guess, because you could imagine U being a constant at 0, then you get 1 over R squared when you square capital R, but then there's R squared from the Jacobian, which would be finite.
Right. That's true, and that could be normalizable. Yeah. But I think no.
But you're saying,
yeah.
I mean, from kinetic energy.
Oops, that's stupid.
Thank you.
Okay. Okay, so if I look at the other regime now, so if R is less than R naught. So in this case, so remember, if we're considering low energy scattering, okay, so as we were saying, as I assumed at the very beginning, I have low energies. So in that case, to a good approximation, I'm going to ignore E in this. I'm going to assume that now I have a potential, in principle, it could be a strong potential in this regime. Okay, so here now I have my potential here. So I'm going to drop the E, and instead I have a strong potential in this regime. Okay. So I mean, in principle, if I wanted to include higher orders, I should worry about the effect of E, but I'm just going to look at the low energy limit. Okay. So in that case, then, okay, so this is this regime. So if I want, so let me just, okay, so this is let me call this my star equation here. Actually, even better, I can put it in a different color. Okay, so here's my equation. All right, so what I'm going to say now is, if I take this is my solution here, my general solution in this regime here. Now, in the case of this potential, if I want to match boundary conditions between this regime and this one here, so what you can see is, like I said, to lowest order, I can ignore E, so this doesn't have any dependence on E. Okay, so what I'm going to claim now is that, therefore, this boundary condition for my solution, let's call it star here, should be independent of E as well, right? Okay, and the way I can write this then is I can say, well, what I want, so the boundary condition, if I'm matching it at R, I want this boundary condition, okay, I want this, let's take this ratio here. I want both the derivative and the U to be independent of E. So if I take my ratio of these, and what I can do now, I can just extend my, I can just take my solution. I could basically take my boundary condition and pretty much anywhere at low R, I can extend it all the way down to R equals 0. I'm just trying to, take this function and work out what this phase shift is. So my statement is really that at small r, I'm going to have something that should be independent of E. And so if I take my ratio of this derivative and the function, I require this just to be some kind of constant that doesn't depend on the energy of my system. Okay. So what I'm going to claim now, this is where my scattering length comes in. What I'm going to define this to be, so you notice that this should have dimensions of length, right? So I have a derivative of U divided by U. Okay, so this ratio should have dimensions of, inverse length. So what I require then is actually, I'm going to define this to be this this minus 1 over A. Okay, I could define it however I want, but this is what I've defined to be the scattering length. Okay, so that's where the scattering length comes in here. So it corresponds to essentially a boundary condition for this sort of larger R solution here. This boundary condition at short R. Okay. Any questions about that?
I have a quick question about that last point.
Yes.
So you define this boundary condition using both U and its derivative. Is that just like a convenient thing you've done to combine two separate conditions, or is it like important to think about it as a ratio?
I think, I think it's basically, I think in some sense it's convenient in the sense that I can just ignore any kind of constants that involved in my solution, and yeah.
So was this defined as like the limit as R goes to 0? Because in principle U at R equals 0 was still going to be 0, even.
Okay, yes. So I should say that when you have the interactions, that doesn't have to be the case. Yeah. Yeah. So as kind of as Leo was pointing out earlier, you can still have it's still possible to have a solution where this is finite at R equals 0 and it's still normalizable, right? But then the question comes in about, what about the derivatives? That connect. In the case of no interactions, the derivatives might be singular. Now, in this case, that could be fine because now you have an interaction at small r. Okay, so any singularity you might have in the kinetic part that due to the derivatives can be compensated by your interaction. Okay, so it's sort of consistent in that case. So in the non-interactant case, you couldn't have this. Yeah. Mm-hmm. Does that make sense?
Yeah, that makes sense. But to be clear though, the u prime over u is, we're just evaluating that at r equals 0.
In this case, yeah. So what I've said is, yeah. So what I've said, I mean, if you like what I guess what I'm claiming in some sense, okay, maybe if I running out of space here. So if I were, you can think of it another way, like I've got my solution here. I could just, as you say, match my boundary condition at R0, or I could just, if you like, continue this solution all the way to R equals 0 and just state this is what it has to be at that point, just a convenience. So I could have put my boundary condition at R0, or I could have just kept extending my function all the way to R equals 0 and said, this is what the boundary condition is, right? So I know whatever it is, I just need to define what it should be at some point at low R. So you can think of it that way. I've even just extended it myself down to R equals 0. Okay, in principle, I've extended it beyond where it may, it's about its regime of validity, but it's just sort of a convenient way of defining it. Because then, now rather than having to worry about an R0 in my, when I go ahead and actually evaluate this, and rather than having this pesky R0 here, I can just send this part to 0. So it's sort of you can also think of it as a convenience thing. Yeah.
But also, as you said, if you're considering short range potentials, then ultimately you can think of R0 going to 0. So then K at low energies, K times R0, which is the argument that appears in the inside sign of KR, sine KR is 0 basically.
Mm-hmm. Yeah. So you can also So you can think of you can also think of the R0 going to 0. Yes. I guess I'm just also kind of emphasizing that if you're worried about that, you can still think about, I have a well-defined R0, and I'm just imagining if I extended my solution past that, into that potential, I can just put put whatever my, define my boundary condition all the way into there as well, if I wanted. Yeah. Mm-hmm. All right.
That's a question.
Yeah.
Did you have to, for the regime where you're considering interactions, did you have to assume S-wave scattering again?
Well, actually, no. In principle, yes. Okay. Well,
Does the scattering fall out when you include higher order partial waves?
Okay, so far I am just considering S-wave. So what I'm doing in a sense is so we know that when we have a rotationally symmetric potential, I can decompose the solutions into different partial waves. So angular momentum commutes with my Hamiltonian, my problem. So I can divide it up into different partial waves. So I can just focus on S-wave, if that makes sense. Everything is S-wave what I'm doing. So I don't have any angular part, but maybe is that what you're asking, or you're worrying about the details of the potential? Is that what you're asking?
So maybe I'm unclear about something, but so did you mention before that the centrifugal part, it dominates unless you just have S-wave scattering?
That's right. Yeah.
But if you don't restrict yourself to just S-wave scattering, would you still be able to have the scattering length fall out of your derivation here?
Right. Okay. Hang on. So this is an S-wave scattering length. So this is only in S-wave. Maybe if that helps.
When you use this scattering length later to get things like the scattering cross section, things like that, this would just be the 4 pi a squared then. Okay.
Yeah. Exactly. So this is only S wave, yeah.
And so one thing I think that just to clarify is that you can have S wave scattering coming from all these channels if they're coupled, but the different partial waves are totally decoupled in this case because you're assuming a rotationally symmetric potential, right? So things get more complicated in other cases, but here I think it's just you have S wave scattering, it's totally independent from the P wave, totally independent from.
Exactly, yeah.
Okay.
Yeah.
Thank you.
Can I ask a question?
Yeah, sure.
So are you able to actually get the value for A from the equation right above it? I mean, U double prime minus 2mr VR U is equal to 0. I mean, are you able to get the value of A?
So you mean like this one here?
Yeah.
From this equation, right.
Yeah.
So the thing is, right, so in some sense, what I'm kind of sneakily doing is I'm saying that the actual details of this potential don't matter when I have low energy scattering. So all I'm saying, okay, so obviously the potential gives me, I mean, the actual potential is connected to this quantity here, but it actually doesn't, like this A isn't actually, it doesn't matter whether, the actual power law dependence of this potential or anything like that. So I wouldn't be able to, just by looking at this equation necessarily, it's maybe not so obvious. I mean, I might end up with something a bit more, if you solve this equation, you would end up with some very complicated form for U, or potentially very complicated form for U within this this range here, within this, for R less than R naught. But all I'm saying is, if I'm only interested in the outside the potential, which is what we see typically, when we look at the behavior of atoms, the large scale kind of behavior, then all that matters is this one parameter here, this due to the boundary condition. Does that make sense? So yeah, so in principle, you might have something, lots of oscillation, might have very complicated U inside, but all at the end of the day, all that matters is what's the boundary condition on my outer solution here. And that we've just argued is just given by this one parameter, which I've defined to be the scattering length. Yeah.
So Meera, maybe a picture may help, like a cartoon of a potential
Yes.
with shift, phase shift.
Yeah. I mean, that okay. So that was what okay. Maybe how about what I do is I'll just continue a little bit further, and then I will actually show you.
Okay, cool.
Yeah, how this. Yeah. So where was I? Yeah. So I'll just write. Okay. So put in the boundary condition. Yes, we've got this S wave scattering length, and therefore, if I just continue this, so I can actually go ahead and I take my U prime over at R equals 0, and just plugging in what that functional form was, what I find is this K times cot KR delta at R equals 0, which is just K cotangent delta naught. And that's what I've defined to be my minus 1 over A. Actually, did I?
Yeah, you did.
Yeah, okay, cool. Actually, I just realized probably I haven't, maybe I should, I'm not sure if I think I forgot to define what the energy was, but in terms of K, so let me just remind you that that's how I've defined my energy here. Okay, all right, so what you can show then is if I take now, if I take, say, this situation where A, this scattering length, which could be in principle either side, K times A is much smaller. Let's take it to be small, so low energy, let's say. So this is much smaller than 1. So what you can show then is that just looking at, I have my, so remember now I have tan, if I just kind of invert this part here. So I have my tan theta naught tan delta naught, equals minus Ka, okay? And if I'm assuming this is very small, this means that that's just basically, I can just expand 10, and then that means that this is just indeed equal just to the phase shift here. So therefore now, if I put that in to my U, I finally have my constant times sine KR minus KA. Okay, so that's my solution, and then now what I can do is I can try and plot this, and hopefully this will give you an idea of this A is doing. So I have my R, and so U as a function of R here. Okay, so if I first just had no interactions, okay, so that would mean this term here, so A is 0, so my delta is not 0. Then I'll just have, just like my sign here. Okay, so that's no interactions. And it's 0 at this point here. Okay. And now if I were to, now I have a phase shift. So let me first, let's say if I shift it like this, looks like I can actually draw it. Okay, so that's an example with interactions. And in fact, this is an example where I have positive A. So what you see actually is it's shifted outwards. So this is with, and it crosses now, instead of actually having my 0 here, I now have my 0 at some point. Well, this is at R equals A here. Okay, so this is where A is positive. I could have also had, if I had, say, a negative A, negative scattering length, this would have been shifted the other way. So it would have been a different color, like this instead. Right, so now I would have had, well, okay, it obviously can't extend quite out there, but let's see. Would have had something like this. Okay. Whoops, now I'm kind of, anyway, but you get the idea. So hopefully, so that would be for A less than 0 here. But you see the point really is what you're doing is the effect of the potential. Okay, so you can imagine, say, this potential is might be very small, some very short range potential here. The effect of the potential is sort of to shift this this wave solution essentially, sort of in and out, or phase shifted essentially, and where this scattering length essentially tells you, essentially where this 0 or this node is in your first node in this wave function is. Does that help? Does that make sense? Yeah.
I guess for a hardcore potential, this would gel nicely with the fact that this first 0 is at the boundary,
yes.
right?
Exactly. Yeah, exactly. So if you had, indeed, so if you had, in that case, that would be a situation exactly where the range of the potential is related to the scattering length. And indeed, yeah, so in that case, yeah, so if you had a hard, if your hard sphere was, say, here, yeah, exactly. So that would be like that. Yeah. So actually, so you can see actually, so if you have positive A, it's like the solution is being pushed out, so being repelled, if you like. So as you might expect in the case if you had this hardcore repulsion, okay? So it's behaving like it has, like you have a hard sphere potential. So for a negative A though, you now actually have it pulled in, okay? So it's pulled in this way here, okay? So that's like where it's being attracted into the potential. So it behaves like an attractive potential. Well, actually, all these potentials we're considering were underlying attractive potentials. But yes, so there it actually behaves like it's attractive interactions between particles. So that's kind of the origin also, how negative A is attractive and positive A is repulsive. Mm-hmm.
Sorry if I missed this, but did you have to assume a form for the potential to get that cotangent solution?
So that probably is sort of over 2 pages. So what we did, we just took this solution here. So so like I said, we we first solved this equation for outside the range of potential when we got this general solution in the S wave case. And then all I did was I took this boundary condition. So I took this and took that at r equals 0. And that's what gave me this. Right. So I took the derivative of u. So the derivative of this would give me a cosine. And then I divided it by sine. So I just end up with this cotangent here.
Okay,
so
so
that's how I ended up, yeah.
we're trying to match boundary conditions between these two different regimes, but you wrote down that R was less than R naught initially, but now we're saying
Yes.
that we're matching the conditions at R equals 0. So that was something that I didn't quite.
Yeah, okay. Yes, okay, right. So I think, yeah, like, okay, so I guess there are two ways of looking at it. Like, well, so as Leo was saying, you could just imagine, well, if R naught is very small, I mean, so it's a very short range potential, effectively, then I can essentially just, just say, like, take the limit where this goes to 0, just take the limit where this R naught is 0. And so that's what gives me this boundary condition. So that's actually, so that's one way to think about it. Okay, so you're imagining it's so short range, I may as well just take R naught to 0. Yeah. Does that make sense? So the other way you can think about it as well, so all I want to do is I want to have I think basically it comes down to we're assuming this is very short range R naught, and we can ignore its we can ignore the dependence on this R naught here. Okay. The other way you can think about it is, well, once again, assuming this is R naught is very small, whether I define my, the boundary condition here or here, it doesn't actually, I'm free to still always define it at R equals 0 if I wish. If it's okay, right? All I need to do is I have my solution, and I just need to work out, essentially where this, where its node is, if you like. You could even think about how you want to use it as a way to fix this, where its node is. But anyway, so basically, it's if you like, it's basically convenient to define it at R equals 0. But it also it has a physical meaning, right? Because you're essentially stating that it's a very short range potential, so it doesn't matter in a sense what this R naught is. Okay, I'm never going to see what this range is at these low energies. I don't know if does that help answer this question?
I guess that makes sense for some potentials, but as we just said, that sometimes the range is related to the scattering length, and then that's not a consistent assumption.
Right. Yes. So I think so the type of okay. So let me put it this way. Well, okay. So I think it's also a matter of the energy of your potential. So let me put another way.
So can I make a comment about notation that I think might be a little confusing if we go to your previous page?
Yeah,
because
sure.
I think U is being used in two different ways in some of these equations, and just in what you've said in words. But to make clear, on the bottom right, that U, even though it's at R equal to 0, you're not really supposed to, it's not the solution U to the real potential, right? So that equation, you're supposed to take the U that is in the right-hand side of equation star, so just that C times sine of KR, and just plug that into the equation. That's not the real U that includes all the wiggles and all the stuff inside of it.
Sure. So if you want, let's see, so I can have, I was trying to avoid using more subscripts, but yes, if you want, let's say, I don't know, maybe I can call this a U, U kind of less than or something to indicate that this is so this is a U that's within the potential, but all I'm interested in is if you like, the U outer. I mean, I could even put it like this if you wish. Yeah. I don't know. Does that make sense? Does that help?
And so the true U that satisfies your Schrodinger equation everywhere is if R is less than R naught, it's U lesser. If R is greater than R naught, it's R.
Yes, that's right. Yes. So I'm essentially just throwing away U less than, but all I've used that equation to show is that it at low energies, it doesn't depend on energy. Well, therefore, to argue this point here. Yeah. Mhm. Yeah.
So maybe this is related to when we talk about resonances, but it seems like you could just make A be positive or negative depending on how you choose to define, your overall phase shift. I mean, there's going to be you could say 2 pi or 2 pi minus, or sorry, you could say like theta or 2 pi minus theta. So what exactly does it mean that it's attractive? Like, what exactly does it mean if A is negative, if I can always just redefine it to be positive?
Wait, okay, so you can't, okay. I see. Right. Okay, so I think, no, that's a good question. So I should say, I'm always, I think I'm always imagining that this, this phase shift is defined between, between a certain, between 0 and 2 pi. It has or at least pi and minus pi. It has a well-defined kind of region. I'm not going to have it multi-valued. So there is a kind of well-defined, there's when I talk about a phase shift, it's going to correspond to a well-defined A. Yeah, that makes sense. Yeah. So no, that's a good point. So that's important. Yeah. So in some sense, so A will have always a well-defined meaning and always be either negative or positive, because I'll always, have a well-defined meaning for my phase shift. Okay. So you're absolutely right. I could always define it modulo 2 pi, but I'll keep it within that range. And I should say I don't. In some sense, we're not really free to choose it will be set by this boundary condition. I've just defined it this way, right? So this A will be linked to actually what's going on. Yeah, we're just not going to solve the whole problem to find out that. We're just going to, we just know it's going to be connected. All we're interested in is we have a potential and it's connected to this A. I'm not going to try and solve this inner part. Yeah. Okay. Any more questions about this? Yeah, this is actually, as I expected, this two-body stuff was going to take most of this lecture. No, but it's good. I think it's important to understand. Yeah. Right. Right. Sure. I mean, delta but I mean, I think it's fine to actually define. I mean, you can do it either way. I mean, but basically, delta is a periodic function, but I think it's always well defined. A that you're talking about. Yeah, just responding to the chat here. Yeah. Okay, fine. Anyway, what we're going to be looking at here is we're always going to look at a situation wherein, I'm jumping ahead of myself, but in principle, you can kind of go through multiple cycles of your phase shift if you go through, if you encounter multiple bound states in your potential. But okay, I'm jumping ahead of myself because I haven't quite got to bound states yet. Let me try and do that very quickly. So what I want to do now is, okay, so I've got my A, and now I want to relate it to my scattering amplitude. Okay, my actual scattered wave. Okay, so now if we come back to the, so if we come back to my radial part, okay. So now if it's S wave, okay, so I don't have any angular part, so the radial part is just my wave function. So my full wave function here is just my U of R over R, okay. And I have a C times sine KR plus delta naught, okay, over R, okay. And, okay, so then you can, if I just kind of divide that up, and so what I can do is I can write this in terms of, just different exponentials. So if I have, so I have so take out my R here, and I have just e to the I k r plus delta naught minus e to the minus I k r plus, oops. And that's 2i here. Okay, so I've just rewritten my sign here. And then I'll just take out my phase vector. So I have I delta naught, 2i, yeah. To the I, okay, R. Okay, so the reason I'm writing it like this is to sort of write it in a form that involves like, now we have sort of an incoming wave and an outgoing wave here. And now you see how this phase shift kind of sits on, actually, sorry, an incoming wave and an outgoing wave. Okay, so now you see how this phase shift kind of modifies this sort of so in the non-interacting case, you would just have this, nicely, this wave incoming and wave outgoing. Okay, and now in the presence of the potential, you actually kind of shift the phase of this outgoing wave. Okay, you modify that. And so now if you compare this, so with this standard expression, so if I take so I have my standard expression, which if I take this, so this is the S wave part of my standard expression here. So, so if I have like, so all I've done is I've taken, I take the standard expression in scattering theory, you have an incoming wave and an outgoing wave multiplied by your scattering length, okay? And now if I take the S wave part, what I can do is I can write it like this. So I have my e to the I r over r, and then I have a minus e to the minus I k r over r. Okay, so for instance, this is in the limit where r is this is large R limit, okay? So for instance, this would be, if you look at it like any standard textbook on scattering, that's what you'd find. And then all we're saying is therefore, if we compare these two, what we're saying is that this is this S wave scattering amplitude here. So if we compare these two, so I have my 2i delta naught. Okay, so I can now relate this scattering amplitude to this phase shift. Okay, and so now finally, if I rearrange this, okay, let's see if I can, which is a useful exercise. You finally find that your S wave scattering amplitude is just related to this. Okay, this is my cotangent delta naught minus I. And then I have finally this minus 1 over A minus IK. All right, so that's, okay, so that's my, finally I end up with this scattering amplitude here.
Is there a K off in the denominator?
Let's see. Is there a
Should
K?
just be, it should just, oh no, maybe it's okay. Yep.
Yeah, no, I think it should be hopefully all right.
It's okay, you're right.
Yeah.
I'm just catching up with your algebra, you're good.
Yeah, sorry, yeah, I spit up a bit when I saw the time, yeah. Yeah, to try and get here, yeah, all right. All right. So this is this standard form here, yeah. All right, so this now finally is how you relate your scattering amplitude to the scattering length. Okay, so it's really just essentially just taking our solution that we did before, what we derived before, and comparing it to the usual expressions that one has where you, for scattering theory, where you have sort of an incoming wave and an outgoing wave multiplied by your scattering amplitude, sorry. And what's important here is that this is a sort of a universal low energy form. You see, like, as I kept emphasizing here, where it just depends on, a single parameter A to describe your scattering, to describe your interactions. It doesn't actually depend on the microscopic details. Yeah. Okay. Any questions about that?
Can I ask a question?
Yeah, sure.
In the, I guess in the line right before you write compare this with that expression there, where you have the incoming wave and the outgoing wave. I think I thought I remember from scattering theory that the incoming particle, shouldn't this be e to the I k z or x or y or something?
Okay, yes. So yeah, so I've yes, this is maybe me being fast. So what the key thing here is I've taken the S wave part of that equation, right? So I've taken the S wave the S wave component of this incoming part. Yeah. So that's why we don't have any angular dependencies, which would be present in the z e to the ikz. Yeah. Or e to the ikz. Yeah.
So you did that. Okay. So you did that in the previous step then.
Yeah, I mean, I skipped. Yeah, exactly. Yeah.
Okay. Thank you.
No worries. Yes. Any other questions about that? Yeah, so essentially these, oops. Yeah, so if the scattering length went there, this would correspond to the S wave. So if this term was zeroing, this would just be the S wave component of my incoming wave. Yeah. All right. Okay. All right, so now I come, are there any other questions or shall I move on? Okay, so, because now we come to the bound state part. Finally, we get to the resonant part, which maybe starts to kind of link back to these discussions we've had about A and how it can be disconnected from the range of the potential. Yep. Okay. Right. Okay. I don't know.
The question is this still under the assumption that Ka is much less than 1?
Right. In what I'm going to discuss now. Oh, were you talking about this part here? You mean which part? Sorry, maybe did you want to unmute and ask? Or?
Yeah, Matthew, did you want to ask?
Yeah. Scattering amplitude. No, yes, no. So this one now, this is for arbitrary. This makes no assumption about Ka. What it does assume though is that, like I said, the energy is small relative to the actual range of the. We're still working on this assumption, but it makes no assumptions about how K compares to A at this stage. Yeah. Okay. Yes, and yeah, okay. And yes, you're right, yes, about the phase shift. I don't know if I mentioned it before. Okay. All right. Right. Okay, so now we have this low energy scattering amplitude. Like I said, it low energy compared to the actual microscopic interaction. Now, what you want now, the point is that now I'm going to claim, and let me argue this in a moment, that bound states, if I'm interested in two-body bound states now, looking at this, if I've just been presented with a scattering amplitude and I want to think about bound states in this potential, in a potential. Now the bound states, I'm going to say, are given by the poles of this scattering amplitude. Oh. So in other words, they correspond to, you know, if I just take the inverse of this, bound states correspond to this condition. Okay. And the reason for that is you can think of it in the following way. So the way we often, you know, we define this wave function, this scattering wave function, you know, like I said, we have a you know, this, and we have like a incoming part, let me just call it incoming, or, you know, scattering part, and we have our scattered part, right? Sort of, and this was the part that depended on, you know, okay, so this would be how it, in the S wave case, I would have, well, or in general, I would have this, where I've just taken the, you know, I have my S wave scattering amplitude here, okay? And now we've defined it, so this is like, we haven't really, you know, worried about normalization. This just has some, you know, normal, you know, coefficient 1, for instance, this one here. So now if I want to describe a state that's bound, so it has no incoming part, there's no free incoming unscattered part, I require this part to actually kind of dominate, to blow up. In the sense that now, well, okay, I've called it scattering part, it's really the interacting part. I want this part to actually, you know, be the whole solution to my whole part of my wave function, in order to describe a bound state that has none of this component. So that requires this scattering length to diverge, scattering amplitude, to diverge, okay? So that's the first thing. That's why we require a pole of the scattering amplitude to describe a bound state. The other thing, actually, okay, so the other thing is you require that, you know, say now when we look at this part here, I want this to correspond to a bound, you know, like a bound decaying wave function. Okay, so I require also that k equals say I times, let's say let me call it q, some real parameter q. Okay, and I require iq not, so this is a real and positive, q, but not notice not minus iq, right? Because the reason is, now if I substitute this in here, if I choose this I times q here, now this will give me this e to the minus q r over r, right? So this will give me an actual bound wave function, and one that decays in space. If I put in the other one, I would end up with something that you know, diverges as I take r to be large. That's not the one I want.
Could K have a real part as well?
Sorry, say again.
Could K have a real part as well?
I wouldn't have thought so. You wouldn't want to. No. I would, no, I think probably not. If you want to have, okay, since I've required E to be the energy, if I want to have a real energy, then no. I would say that, yeah.
And so there's another question from Alex asking, why are we binding K to be purely imaginary?
Right. So why do we want it to be purely imaginary rather than, right? Okay. So I guess there are, well, two things. So the first thing in some sense is, like I said, now I'm describing it. If I want to describe a wave function that is bound, like a state that's bound, I want something that decays in space. Okay, so I want something, you know, what this is describing basically is, now, you know, I've got my two particles, and, you know, they want to actually, you know, they're sort of generally found to be close together. They can't actually be far apart from each other, okay, or not too far apart. They're sort of bound in that sense. They're not gonna, I'm not going to find them infinitely far apart. Okay, so I want this kind of state here. Okay, right. So the other thing is that if I take this now, what I find, remember if I had energy which was h bar squared k squared over 2 mr, that gives me now minus h bar squared k squared over 2 mr, right? So now I switch to the case. Now what I've found is that I'm looking at an energy that is less than 0, okay? Which also kind of matches with our expectation for a balanced state, right? So rather than a scattering state where you kind of have energy greater than 0 coming in, now I have an energy which is actually sitting in negative energy sitting in my potential, which is bound, okay? Or sitting below the continuum, if you like, below the scattering states. Does that make sense?
And I guess, so you can have either a real part or you can have an imaginary part, but you can't have both because you'd get a complex energy out of this.
Correct, yes, that's right, yes. Yes, that's right. Or at least, yes. At least we're not worrying about losses and things like that, yeah. Okay. All right, so final step. How do we, now if we, remember I've made this statement here. So now I can work out actually what this Q is in terms of A, okay? So therefore we have minus 1 over A, and now I put in my minus I Q equals 0. Okay. All right, so therefore, okay, so that gives me plus Q here. So therefore I end up with Q equals 1 over A. Okay. Right, so what sign of A do I have to have if I want to have a balanced state? Now I'm asking you guys a question. What does that tell me? What sign of A? Can I have a balanced state for any sign of A, or does it have to be a particular sign of A, the scattering length?
It has to be positive?
Yes, that's right. Yes, so because I've assumed, remember at the beginning I took Q to be positive. That's right, yes. Yes, that's right. So I only have balanced state when A is greater than 0. That's right. And in this case, then we have energy, which is minus h bar squared 2 mr A squared. Yeah. And so now if I just do my little plot here, all right, so whoops, getting there. I have 1 over A and have my energy. So let me see if I can draw. So you have something that looks, it's not very nice. Hang on, let me try and draw it a bit better. Something that looks like this, so you have a quadratic function, but for negative A, there's no balanced state on this side, yeah. So what you see actually here is that the balanced state actually appears at when 1 over A is 0. So in other words, when the scattering length diverges. So the scattering length diverges at the appearance of a balanced state. Okay. So the other thing I would just emphasize here is you might be wondering physically, why is it that a balanced state occurs when it looks like you have a repulsive scattering length A. And the reason, the way you can think about it is that, okay, so we're mentioning we always have some kind of underlying attractive potential, but depending on what the parameters are, we can, depending on what the potential is, you might have a balanced state in your potential or may not. if you have a bound state in your potential, like what you would find then is that the scattering states then must be orthogonal to the bound state in your potential, right? So imagine here's your kind of whatever, some kind of potential here. You have your bound state here. The scattering states now coming in have to be orthogonal to this bound state here. So what that effectively means is that this bound state is going to repel your scattering states. So that's kind of like why you can explains a bit like why it behaves like a repulsive potential. That makes sense.
So there's a question from, oh, sorry. There's a question from Eduardo. Eduardo, maybe just unmute yourself and ask.
Sure. Yeah, I was going to say that isn't the cross section like the real physical quantity rather than the scattering length, in the sense that when you have a resonance, A diverges, but sigma remains finite. And like, for example, if you look at particle physics or nuclear physics papers, they just use the cross section, which is a measurable finite quantity. So, I mean, I guess this is something because a lot of interactions in AMO are S-wave. We just use the scattering length or A like as the natural parameter. But could you comment on this?
Yeah, sure. Okay, so let me. Okay, so this is maybe getting into a deep question here. Yeah. Okay. So right. Okay. So I think probably what you're saying then is okay. So let's say, so you're saying, what if I just why not the cross section? Let's consider the cross section. Okay, and so that's related to the essentially your MI scattering length. Let me write it so like this, just to be. So it's well, at least proportional to my scattering length, absolute value squared. Okay. And I think what you're getting at here is the fact that you see now in principle the cross section you're going to be measuring is going to involve, say, a range of energies in general, right? It might be the gas might have a temperature. You might be the various things that could set the typical collision energies. Okay. And so okay, so if I took, say, let's take the case where 1 over A equals 0. What you can see from the scattering, amplitude coming back to this equation here, if I set, so I set 1 over A to 0, I still have left over this this energy dependent part here, or this K dependent part, right? So I'll still have something. So if I even, so if I take the resonance case, I'll have something that looks like 1 over K squared, right? So what I'm trying to say here is that, you're right that in general, if you go out and measure a cross section, you'll find something. Okay, you'll probably see some peaky structure around resonance, but you'll generally see it cut off somehow or finite. And I think that really is to do with the fact that you never really reach zero energy, and you'll never really, or rather in practice, you'll never look at exactly zero energy. You'll always be at some finite energy. Is that maybe that kind of, that would be my kind of response to that?
Yeah, no, I think that's great. In the sense that, in general, I feel very anxious when people say like, oh, this just goes to infinity, or like some physical quantity goes to infinity, like, because in general, nature doesn't like infinity things. But like using the language of the scattering length diverging is extremely useful for what we use. We use, but I just think it was like nice to make this connection that like the physical measurable thing, it's a finite. It's just a finite number, right?
Yes. Yeah. No. You're absolutely right. Or at least, yeah, in practice, yes. You can probably see how it depends on, if you lower the temperature, you can see the trend towards it trying to diverge, or lower the energies. But yes, in practice, yeah. Okay, so one issue, let me see. So someone, Matthew's saying one issue is that sigma fails to distinguish between, exactly, the positive and negative scattering. Yeah, that's right. Yes, so that's also correct. Yes, that this, of course, the cross section doesn't tell you the sign necessarily of the scattering length. Yeah. Mm-hmm. All right.
So you can follow up on so if the scattering length has information that goes beyond the cross section, and we know how to physically measure the cross section, but then where does this information about the sign of the scattering length show up if it doesn't show up in the cross section? Can you give an example of a physical measurement where it shows up?
Okay. Well, okay, yes. So I suppose, well, let's see. So I guess if you start measuring like energy shifts in a gas, that would be one, like say, okay, what I've been looking at in particular, this is a very clean example, is the case where you have, I mean, you can do it in many different cases, but the case, say, where you take one, say one type of atom, like one type of fermion, let's call it red, and put it in a Fermi gas of the other type, say the black or the blue fermions. Take so a single type, red one, put it in impurity, put it in your Fermi gas, and look at how its energy shifts as I vary my scattering length. And yeah, what you can see then is that the energy shifts either upwards or downwards depending on the sign of the scattering length. So that's one example. Yeah. So yeah, so looking at the energy shifts somehow in spectroscopically. Yeah.
So there are a couple more, or there's one more question. It says you commented on this, or Jaron, do you just want to ask?
Hi. So I just want to hear again, like about this, the results basically. Why are we confined? Why are we constricted to repulsive interaction for bound states to occur? They're like a intuitive way of seeing this, basically.
So you mean you're talking about this argument here, or you're talking about the physical argument I gave before about?
I think you gave an argument. I just missed it.
Okay, sure, no problem. Yep, that's right. So the argument was, yeah. So you imagine you have your potential, and it has, say a bound state sitting here or close by. So the statement really was that if you have a bound state in your potential, your attracted potential, and now you have, say, another particle coming along and scattering off this potential. This scattering state now, so this, these are all states that need to be orthogonal to each other. These are different eigens, if you like, you can think of different eigenstates of your problem. These scattering states have to be orthogonal to this bound state in your potential. So that means in some sense that they effectively have to be, that effectively leads to them being repelled. Like you have the wave function is modified so that they have no overlap with this bound state. So they effectively experience a repulsion. That's why a bound state corresponds to effectively what looks like a repulsive scattering length, so a positive A. Yep, does that make sense? Yeah. So if you can, yeah. Yeah.
And Meera, just as a heads up, we're running towards the end of time,
yes.
So we'll want to leave time for some final questions here.
Right. Okay. Right. Yes. Okay. So the only other point I wanted to make, I didn't want to sort of go on too much about the Feshbach resonance, because there's that you could give like a whole lecture on probably by itself. The only thing I wanted to point out here is that the main thing I wanted to point out here is what all this analysis I've done here, about those bound states and so forth. This really only applies. What I'm implicitly assuming here is that I'm always in the low energy regime, right? So I've derived this scattering amplitude assuming very low energy scattering. And so what this automatically means, if I'm going to have a bound state that is also low energy, I have to have this energy here has to be this energy here has to be smaller than the energy scale set by the actual range of my potential, right? So this means also that this scattering length has to be much larger than R0. That's what I'm assuming in all of this discussion right here. And so the way you achieve that now in practice is with the so-called Feshbach resonance in your cold atom case. Okay, or rather maybe the way you achieve that is that you need to be in a resonant situation where, like I said, there's either, say, a bound state nearby or is just about to form. Okay, so you have a bound state and a potential that's, so you're in this regime where, as we noticed, the scattering length can be very large when a bound state appears. So if you have a potential with a bound state nearby, you're automatically in this situation here. Okay, and the way you can achieve that is with this Feshbach resonance. I mean, where you can tune that is with the so-called Feshbach resonance. I'm wondering though, given that I'm short of time, should I just pause here, or do I? What do you think, Hayden? Should I?
So I think probably it's better to pause here, and then we can continue to have some discussion. We can take a few extra minutes, and people can continue to ask questions, and then you can pick up in the next lecture. But this seems like it's probably a good place to stop.
Okay, sure. Now sounds good.
Yeah. But the floor is open. So further questions. We've had great discussion.
Yeah, no, sounds good.
I have a question. It seems like that bound state condition only has one solution, but there's obviously potentials with many bound states. So where's that disconnect?
Yes. I mean, so in some sense, like I said, it's a good question. So it comes back to that point I was making about this is only really valid in this low energy setting. So in other words, this kind of discussion that we're having here only can really describe the situation where there is a bound state nearby. It doesn't describe any of the kind of details of your potential. So it doesn't describe any of the deeper bound states in the potential. So really this kind of analysis can only describe, say, a single bound state that's nearby the continuum. Okay. The other way you can think about it, I mean, so that's one way. The other way you can think about it is, like I said, we're coming back to this idea of a short range potential. And how we were kind of arguing how, let's just take the limit where let's forget about the range. Let's take the range R naught to be very small, blah, blah, blah. The limiting case of this is, I mean, if I take the limit of this, I end up with, like if I didn't quite get to all this, but if I imagine, I have my whatever R naught, my very short, small, very short range, my short range kind of potential, and I can imagine, say, taking a situation where I take it to be, shorter, take the limit of this to be a shorter and shorter range potential, right? So in the end, I'm going to end up with essentially something that approaches this delta function. Okay, so I make this shorter and smaller, and I make this sort of deeper and deeper, so I can still support a bound state. Okay, so at the end of this kind of process, I'll end up with essentially something that approaches my delta function, and that only has one bound state solution. Okay, so that's kind of the other. Well, I mean, that's kind of the other thing where, I mean, it's related to this essentially this assumption we've made that we have very short range potential and very low energy scattering, and we don't care about the details. Okay, so essentially taking this kind of limit.
So let me make sure I understand that. So definitely sure. This formula for the energy, relating the energy to the scattering length, that required that we're in this kind of limit. But the earlier discussion, for example, where you were talking about the scattering amplitude having poles at k is equal to IQ, that does not rely on this, right? And this would still, you'd get poles from all the bound states?
No, you're absolutely right. Yes, that's right. If someone gave me the if someone gave me the exact scattering amplitude or this exact function, and they'd have to give it to me for also imaginary k as well. So somehow you'd have to, you do a calculation and you'd hand it to me. Then indeed, yes, you're absolutely right that in general, this statement holds for a general scattering amplitude. Just that the analysis I've done here, of course, where is it here? So you're right. So if I had the exact scattering amplitude, I would see all the different bound states. But now because I've only you've given me I've just used this low energy part. That's the approximation essentially, or at least the limit I've taken here. Yeah. No, you're right. Yeah, that's true.
Other questions?
So I'm a little confused. So earlier we argued that for a less than 0, we had a attractive potential, right? And the wave
Yes.
function is attracted towards the box. But now here it seems that if you have a bound state in an attractive potential, you still get repulsive A greater than 0. And I guess I'm confused between those two things.
Right. Yeah, sure. No. That's why that's what I was trying. That I also found confusing when I first heard about it. So yeah, so I think the point really is that when there's no bound state, okay, and so like I say, you have this attractive kind of behavior. What you're really, the way you can think about it is that this attraction is sort of the potential trying to form a bound state, but not quite succeeding, if you like. So yeah, so if you like this pull towards the center, it's close to forming a bound state, but it hasn't quite got there yet. But now once it forms the bound state, okay, you have this resonant behavior. Once it forms the bound state, like I said, then you're in this situation where now you have the state in the potential. And now the scattering states coming along are going to have to be orthogonal to that state that you've formed. Hence now you've got this repulsion, if you like, almost level repulsion happening. Does that kind of make sense? So that's the kind of the way I see it, at least. That I mean, there's basically always an underlying attractive potential. But now if we're just thinking of the low energy kind of scattering behavior, that's kind of what happens. That on the one hand, it's trying to form the bound state. Once it's formed the bound state, okay, the bound state is there, and now you're kind of being repelled by that bound state in there. Yeah.
So if I want, I guess, negative scattering length or attraction, then what I can do is I can be away from a bound state and then presumably.
Yeah, so you can tune it, or if you want to have very strong attraction, say so large and negative scattering, you can tune it so it's about to form a bound state that hasn't quite managed yet. Yeah. Exactly. Yeah.
Earlier in the discussion, we had a functional form for that U, the sine of KR, which has infinite number of radial nodes. But in realistic potentials, we know that there's only finite number of nodes. Is there some explanation for that feature?
Okay, right. I think, okay, so the way to see that, okay, so you're wondering about, let's say, yeah, so you're saying this one, say, okay, yeah, okay, so this is the behavior outside the potential. Sorry, I think the way to understand that is you should think about maybe, so this is a, okay, so this depends on, these are a series of solutions that depend on your energy K, right? So if you were to take like the lowest energy scattering solution, so that would be essentially K approaching 0, you would have like no nodes essentially, right? So that probably fits in with your idea that the lowest energy solution, or at least outside if you're thinking about general quantum mechanics, the lowest energy state is the one with like the least number of nodes, okay? And now when you start increasing, if you're going to higher and higher energies, you essentially increase the number of nodes in your problem. So you can think of this as essentially being related to how energetic your scattering is, the number of wiggles that you have. Does that make sense?
Yes, that makes sense. And I also realized that I was mistaking these scattering states for bound states in my
right, yeah. Okay, got it. Yeah. Yes. I was wondering actually whether, okay.
So in your expression for the scattering length, like K cotangent of delta naught was -1 over A.
Yes.
If it seems, if we take, I mean, that only works if we assume that we have E greater than 0. Because I mean, if E is less than 0, then we're going to have an imaginary scattering length if K is imaginary.
Let's see.
But I guess our ansatz might have been that it was, I guess it would have been a cinch instead of a sine. But
yeah, I think things, okay, we'd have to, okay, no, it's a fair question we'd have to go through. I think it should work out, hopefully. Let's see. So yeah, I mean, we can double check that, but I would think that it should still work out. But there may be some, we have to be a bit careful about things diverging and so forth, like scattering length. Oh, sorry, scattering amplitude. I know I keep calling it scattering length diverging. No, it's a good question. It's probably a good thing to sort of go and check and see how it works. Yeah. But like I said, the caveat is that there is this infinity going on here. There's this limit we're taking here. Yeah.
All right, so that's probably a good place for us to stop and take a break and eat dinner or breakfast or lunch or whatever, and before we go to the public lectures. So thank you for the great discussion, Meera, and I guess we'll look forward to your next series in these lectures tomorrow. Is that right?
Is it tomorrow? I think it's even
Thursday.
Thursday.
Thursday. Okay. Thursday and Friday. We'll see.
Yes, that's right. That's right. That's right. I'm getting confused about days.
Well,
Yes,
I don't even know what today is. So, all right.
All right.
Thanks, everyone. And of course, if you have additional questions, bring them next time or put them on the Discord, and maybe we'll pop in and have a look there. So, see y'all.